After white full-rate CDR, let's switch to white half-rate or quarter-rate CDR. Again, in half-rate CDR, the clock used for data recovery operates at half the data rate, which is particularly advantageous for system handling very high data speed. Here are some reasons why half-rate CDR is preferable, and you should apply it to your needs. First, before talking about the half-rate CDR, let's review a full-rate clock frequency challenge when the service data rate keeps increasing at very high data rates. Generating and managing a clock that operates at the full data rate can be challenging. By using a clock at half the rate, the design can avoid some of the difficulties associated with the generating, distributing, and synchronizing a high-frequency clock signal. This frequency reduction in clock makes the circuit design easier and less prone to errors due to clock jitter or skew. In addition, operating at a lower clock frequency, resulting a lower electromagnetic interference EMI. This is beneficial in environments where minimizing EMI is important for maintaining system performance and ensuring compliance with regulatory standards. Therefore, second, we want a simplified design with reduced complexity and challenges. Even though the full-rate clocking has the minimum number of clock phases, without the multi-phase generation and phase corrections, the half-rate CDR reduces the complexity of critical circuit components, such as the voltage control oscillator VCO and feedback frequency divider FBDIF in the phase loop PO over high-speed clock source. Keeping these critical blocks operating at a lower frequency makes their design and implementation more manageable. This can lead to a more robust and reliable system, especially in high-speed communication links. Third, in half-rate CDR, the receiver clock runs at half the data rate, which relaxes the timing requirements for the clock recovery circuit. This can further simplify the design and implementation of the CDR circuit, especially at very high data rate, where timing constraint becomes more challenging. Why is the timing being so difficult in the input data sample and its retiming? Look at the full-rate bang-bang PD image for 5 seconds. Also, think about the input sensitivity for 5 seconds. Correct. The input D-in is a CML level with a varying input swing. A lower input swing, the longer time of the flip-flop 1 or strong-arm latch may take more time to generate to a CMOS level at the output A. In other words, the full-rate clock CK only has half UI for the rejection time, which may have a less input sensitivity than the half-rate clock CK2, which provides a full UI for the rejection time. At the same input swing, the half-rate clock provides twice rejection time to the CMOS level. Then, the data rate can be ballpark go twice faster. In addition, under the same input swing, the half-rate clock may meet timing requirements of the setup time at the retiming stage easier than the full-rate clock. 6 choice time is available in the half-rate. What else could improve the clock jitter? Bingo! Half-Rate CDR allows for improved clock integrity by reducing the effect of clock jitter. Since the clock operates at a lower frequency, the CDR would have a less intrinsic half-rate VCO random jitter than the full-rate VCO. Why is it critical? Think about the tracking bandwidth of the CDR for 5 seconds. Yes, the CDR has a limited bandwidth of a low-pass response. Therefore, any intrinsic jitter above its tracking bandwidth cannot be tracked by the CDR and would directly show up the random jitter at the recovery sampling clock. Then, the equivalent I width is shrinking with a higher BL rate. In order to reduce the random jitter to the clock source, we must improve the VCO phase noise, clock buffer jitter, and any critical noise source from the PL. So, a half-rate clock would be easier to achieve a low jitter clock source at a lower frequency than the full rate from a system point of view. In addition to the RJ, what else should we improve? Think about the PD accuracy image for 5 seconds. Correct. The memory effect or hysteresis of the sampler in a PD comes from opposite polarity between the previous and the current samples. For an ideal sampler with a clear out reset, you should see the differential output toggle from 0 to 1 right after the input just passed the differential 0 voltage from the rising ramp. On the other hand, you should see the differential output should toggle from 1 to 0 right after the input just passed the differential voltage from the falling ramp. But for a real sampler without clear reset, what you expect? Think about the flipping image for 5 seconds. Bingo! You should expect the differential output toggle from 0 to 1 after a delay time, delta TR, over the time when the input passed the differential 0 voltage from the rising ramp. Then, the sampled voltage V in R will be the minimum input voltage to flip the output from 0 to 1. Similarly, the V in F will be the minimum input voltage to flip the output from 1 to 0. The hysteresis of the input voltage is V in R minus V in F, which is usually the static input sensitivity of the sampler, and that's usually not quite useful, since the clock to Q timing of the sampler was not included. So, we rarely discuss this hysteresis voltage. How about hysteresis time? Right. The hysteresis time is the very critical for any CDR blocked in the transition of the input data. Take the Alexander phase detector as an example here. If the transition reference would lock to the TR from 0 to 1 and TF from 1 to 0, then the data-dependent jitter DDJ of the recovery clock is introduced by the edge sampler's hysteresis. The higher edge sampler's hysteresis and the CDR would generate a higher DDJ recovery clock. Therefore, to avoid the excessive DDJ from the input, we must minimize the sampler's hysteresis as little as possible by trading off its speed. If we like to keep the required data rate, but reduce the hysteresis time, what can we do? Think about the reset time image for 5 seconds. Bingo! Just increase the reset time to clear out the hysteresis as much as possible. let's review the reset phase and sample one more time. The differential signals at x, y, and p minus q are near zero during the reset phase because both M5 6 switch pull to VDD and M9 switch show nodes P and Q. The more time we perform in the reset phase, the less residual hysteresis we would have. Therefore, a half-rate clock can provide twice reset time as well, clearing the hysteresis than the full-rate clock. Then, the half-rate clock would have a less DDJ than the full-rate clock inherently. Even if we are talking about the NRZ CDR, if there's any ADC-based digital CDR, the lower sampling rate at the front-end ADC would also reduce the DDJ compared to the full-rate sampling ADC. In the first beginning, we know the design changes complexity of a high-speed clock frequency. Therefore, the reduced clock rate in half-rate CDR can lead to a low power consumption in the receiver circuitry, as the clock generation and distribution circuits operate at a lower frequency. This power efficiency is particularly beneficial in applications with strict power constraint systems. For example, half-rate CDR is an attractive option in mobile devices and data centers, in addition to the low power and low complexity. What's the critical target of the RX CDR? Think about the tolerance image for 5 seconds. Great. Jitter tolerance. Since the receiver's clock is running at half the data rate, it inherently has more tolerance to timing jitter and phase variation in the incoming signal owing to a less intrinsic RJ and less jitter generation from the DDJ. Even though the half-rate CDR has more latency than the full-rate, there are other less jitter sources in half-rate that can still make it have a better jitter tolerance than the full-rate one. As our studies block we discussed, when the data rate continues to rise, the full-rate CDR becomes more difficult to implement due to the limitation of current technology in generating and handling very high-frequency clocks. Fortunately, the half-rate CDR offers a scalable solution by having the clock rate, which can accommodate future increases in data rate without requiring fast clocking technology. Again, when the full-rate CDR hits speed limits, the half-rate CDR can be advantaged in improving power efficiency, relaxing timing requirements, and improving the jitter tolerance with the less DDJ and RJ for important design considerations. Similarly, if the half-rate hits the speed limits under the available technology, we can keep scale down the quarter-rate over low-rate CDR. Here are a summarized image of why you may need a half-rate over quarter-rate CDR. Again, the choice between full-rate and half-rate CDR often depends on the specific requirements and trade-offs of your target applications. Even though the half-rate CDR introduces complexity of multi-phase generation correlations with a longer latency than the full-rate CDR, the half-rate CDR can achieve a low RJ and DDJ with a low power complexity solution. So, fortunately, we can keep increasing the data rate while scaling the clock rate to 1/2, 1/4, or even 1/8. if the user technology or process does not scale well. Just give you a simple rule of thumb. If the data rate is low enough, pick the full rate. If the data rate is high enough, pick the half rate. If the data rate is even too high, pick the 1/4 rate or 1/8 rate. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback and appreciate your comment down below. Lastly, please share the video link with the people who may be benefiting from it.